All right, so in this video, I'm going to talk about charge sharing. Charge sharing is an interesting property of capacitors. It's used in memory for sensing the amount of, sensing the data that's stored in a memory cell, specifically in DRAM. I can get into that in another video at some point, potentially, if anyone's interested. But let's just say I've got some capacitor, right? And that capacitor is charged initially to some voltage, VC1. Let's just say it's 1 volt. All right. And then let's say I've got another capacitor sitting over here, and let's say that this is a 1 microfarad capacitor. Okay, and then let's say I've got another capacitor that's sitting over here, and let's say that it's a 2.2 microfarad capacitor, and let's say that it's initially charged. Here, let's move this here. Let's say this guy is initially charged to some voltage VC2, and let's say that this is going to be 2 volts. All right. And so the question becomes, if I have a switch between these two capacitors, so right now they're not connected to each other, right? So this node is sitting at 1 volt, and this node is sitting at 2 volts before the switch closes. The question is, what happens when the switch closes, right? And so I think it's probably best to draw the equivalent circuit when the switch does close. So let me go ahead and do that. All right, so when the switch closes, what my equivalent circuit looks like is, let me erase these initial conditions. My equivalent circuit looks like this. Okay, so now I have two capacitors in parallel, right? I'm left with my initial two capacitors that were disconnected from one another are now connected in parallel, right? Maybe it's not as obvious, but if I delete these grounds, I can equivalently draw this just like this and then put ground here, and that's the same circuit, right? So now they're connected in parallel. You can see that I've got a node here that they share, and I've got a node here that they share. So theoretically, if two things are in parallel, they have to have the same voltage across them, right? That's the definition of parallel components. But VC2 had 2 volts across it, and VC1 had 1 volt across it. So what the heck happens? How can we get, if there was 1 volt here and 2 volts here, what voltage would we have here? That's the question. That's what charge sharing sort of discovers or uncovers, I should say. And we can figure that out using charge sharing or using conservation of charge. So this concept of conservation of charge, let me write it out. It states that the amount of charge before the switch closes is equal to the amount of charge after the switch closes. Okay, so that's conservation of charge. And so what that means is that in the, with the initial conditions that I was given, I can use CV equals Q to figure out how much charge was stored on this capacitor initially, right? If I take 2.2 microfarads times 2 volts, I know that my initial Q, I'll call it QI of capacitor 2, was, so 2 times 2.2 or 4.4 microcoulombs of charge, right? And so the same goes for the first capacitor. So QI1 would be the voltage of the first capacitor multiplied by the capacitance, or 1 microcoulomb. Okay, so my total amount of charge would be Q initial of 1 plus Q initial of 2, which would just be 5.4 microcoulombs. That's how much charge I am storing at the beginning. And that's exactly how much charge I need to be storing at the end, because conservation of charge says that the amount of charge before I close the switch is equal to the amount of charge after. Okay? And so if I close the switch and I have these two capacitors in parallel, well, what I'm left with is a new equivalent capacitance. My new equivalent capacitance here could be replaced by a single capacitor. If we remember from the previous lecture on series and parallel equivalence, I can just add these two values. So this new equivalent capacitance is just 3.2 microfarads, right? Well, I know that my new capacitance is 3.2 microfarads. I know the total amount of charge is supposed to be 5.4 microcoulombs. So if I just rearrange this equation to solve for V, I can figure out what this node voltage is, okay? So V is going to be my new capacitance, 3.2 microfarads, right? Or sorry, V is, if I were to rearrange this, it would be Q over C. So if I write my final charge, which I know is 5.4 microcoulombs, and my new capacitance, which is 3.2 microfarads, well, the micro cancel, so I should get units of just volts. And let me throw that in my calculator real quick. I just need to do 5.4 divided by 3.2, and I get 1.6875 volts, or 1.69 volts is close enough. Okay? And so that's all charge sharing is. It's just going through that process. In the next video, I kind of solved an example here by just as I was explaining it. But in the next video, I'm going to solve another example of a charge sharing problem. And yeah, for now, I'll just leave this video here. This was me explaining charge sharing, and I sort of solved an example. I'm going to go through another example in the next video.